Bismillahirrahmanirrahim. Welcome to the new lecture of physics. So today we are going to study about electric flux and electric flux density. So what is electric flux? Let's see. This is a kind of a area. Okay, this is area, right? And we have a charge, let's see, and this charge have electric field lines. This charge have a electric field line. So we have an electric field line and we have a area. Okay, so when number of electric field line is passing through the unit area, this is called electric flux. Okay, simple. So in electromagnetism, electric flux is the rate of flow of electric field line through a given area. This is called electric flux. The total number of electric field lines of a force passing through the unit area of the surface. So electric flux is a scalar quantity and electric flux is denoted by this sign. Keep in mind, this is electric flux sign, and the unit of electric flux is Newton meter square per coulomb, and we can also be used voltmeter. So what does it mean? Another definition which is simple. When number of electric field line is passing through the unit area, number of electric field lines passing through the unit area. So simply we can say like that a dot product of a electric field line and unit area is called electric flux, and we can also be used like that, E A cos of theta. So this formula can be used. So from this formula you can derive unit of flux. You know about the unit of electric field, you know about the unit of area. So solve it out. At the result you can get this unit. Okay, so mathematically the electric flux is defined as, I told you before, the dot product of electric field intensity and the vector area is called electric flux. This is the formula, and we can also be write like that, where theta is the angle between electric field intensity and the area. Let's see, this is your area. This is like a what can I say, let's see, this is about area, just simple, and this is electric field line. So how many electric field line is passing through this unit area? And so let's see why the area, direction of area is in this way, because the surface is like a band here, the surface is like this one. So how will be the, so the midpoint always show the area of the direction of area. So the midpoint, this is, and this is the, if you can see, this is coming to the above. So this is area. Okay, and electric field line is passing like this way, electric field line is passing like this direction. So this is electric field lines, electric field intensity, so it make an angle of a theta. So that's why you can use EA cos theta when you are using cos theta, so no need to write dot. Okay, so flux is equal to EA cos theta because of this formula. Once you have the area in a straight, like your surface like this one in a straight, and this is the midpoint, and the direction of area is, sorry, it's like, I'm going to be correct this one, like this is your area and the direction will be straight, and this is your area. This is direction of area, and if an electric field line like in this way. Once your area is in the box shape, let's see, your area is in this shape, let's see, this is your area. So where is the middle point? This is the middle point, and what, and how is the direction? The direction is like above, you can be make it like down. Okay, so this is the direction. So how can find the area direction? How is will be the surface? Just take the midpoint and draw the area direction of area. So now coming to the properties of electric flux, we have a maximum flux, we have a minimum flux, we have a zero flux. Okay, so for a maximum flux, so the direction of area and the direction of electric field line will always be in the same direction. So when both are in the same, so what should be the angle between them? The angle will be 0. So E dot A, EA cos theta, and theta is equal to 0 and cos 0 is equal to 1. So you have a maximum electric flux when your area, your surface is perpendicular. This surface is perpendicular to the electric field lines or electric field intensity, where the angle between the electric field intensity and the area will be 0. So coming to another zero flux, when we have a zero flux, when the angle between the electric field lines and the direction of area, the angle between electric field and area is 90. So in this case, theta is equal to 90, E dot A, EA cos theta, cos 90 is equal to 0. So you have a zero flux. So what he can say? So he is saying that when your surface is parallel, to the electric field line. Let's see, you have a book. Let's see, this is your book. Okay, this is your book. So this is a surface. When this surface is perpendicular, you have a maximum work done. When this surface is parallel to the electric field line, the direction will be up. So it means the direction is up. So the theta is 90. Okay. So in this case, you have a zero flux. So coming to the application of electric flux. So electric flux through a sphere. So keep, and this thing is in importance. So how we can find the electric flux inside a sphere or a ball or a circle and so on. So electric flux through a sphere. So consider a small positive point charge Q. Consider a small point charge Q placed at the center of a closed sphere. If we are taking a charge here, okay, this is a charge Q. So this sphere is in the shape. So the relation is not applicable in this situation because the direction of electric field intensity is varies point to point over the surface, because the electric field here it's going to be changed at any direction, because it's not to be like a plane surface, so it's going to be changed. So in this case, what we can do, in order to overcome this problem, the sphere is divided into a number of small pieces. What we can do, we are doing to divide this sphere into small pieces. We are doing into divide the sphere into small pieces, and at the end what we can do, we will find the flux of a one piece, then we will add all the flux of all the pieces. Okay, and this is another. Okay, so what we did, we divide the surface of a sphere into small pieces of a area. So the direction of electric field in each segment of a sphere is the same, like a outward. Everywhere it will be outward, everywhere it will be outward. Okay, so let's see, we are taking this point, this piece of area. Okay, and we are going to be find out the flux. So now we will determine the flux through each segment, and this segment we selected, and we need to find the flux of this segment. And what we can do at the end, we add all the pieces. So electric flux through a first segment, this is a segment which can set A. Okay, and this is the unit vector of area, and this is electric field. So flux 1 is equal to E dot A cos theta. So direction of electric field line, electric field intensity, and the direction of area, both are the same. So theta is equal to 0. So EA cos theta is equal to 0, cos 0 is equal to 1, and so flux 1 is equal to this, and theta is equal to 0. So A is we mentioned in this slide, and we said that the direction of electric field in each segment of a sphere is the same. So mean in every segment, once we are going to find out the direction of area, so direction of area and electric field will be the same. Okay, so this is the flux 1 E dot E. Just don't use A, because you always use the, don't use the dot, just like a flux 1 is equal to EA. So now coming, what we can do, we are going to find the flux at a piece 2, at a segment 2. So EA, again the same one. So you can be differentiate by A1, A2, A3, but you cannot be, because all the pieces are the same, all the pieces have the same direction. So we just say flux 1, flux 2, flux 3 and flux 4. Okay, but we can you say that area 1, area 2, area 3, area 4, because area is going to be changed or not, but flux electric field lines always be same. So similarly, the electric flux through other segment, so flux 3, flux 4, flux 5, flux 6, 7, 8, 9, if you can use A3, A4, A5, A6, F2, AN, you can it, but you cannot be used, it will be the same. Okay, so what we are going to do now, we are going to add all the flux of each segment. So being a scalar quantity, as I mentioned before, that the flux is a scalar quantity, so the total flux to the sphere will be equal to the algebraic sum of all these flux. So what can say, so we have a number of a flux, so the total flux is equal to sum of all the flux which start from I, and I start from 1 to N. N mean it may be 4 area, it may be 5 segment, it may be 6, it may be 7, 8, 9, 10 segment or pieces. So N is your limits. So I just use N because we have N number of. If you have a 6 segments, you can use I start from 1 to N, I start from 1 to 6, or you have a 10 segment, you can use I start from 1 to 10 and so on. Okay, so this simply simple method how you can going to add total all the flux and conclude the total flux. So this is a flux, and you know about a flux is equal to EA. Okay, and we can also use E is constant, because we have a sphere and E is always is same in everywhere, because we have a sphere. Okay, so E is constant, so it's come out. So what is going to be changed? Area is going to be changed. Area can be A1, A2, A3, A4, A5, A6 and so on. So what we are going to do, so E is constant, come out, and area is going to be changed. So we say that area start from I to 1 to N. Okay, as I told you before, that you can be write A1, A2, A3, A4, because area is going, you can be choose it as a constant, you can be choose it a variable. So as according to the formula of electric field intensity, we can be write in this form, and we can also be write in this form, as you remember the formula. Okay, so we have electric field, and the electric flux is equal to this. So put out the electric field here. So this will be here. So 1 divided by 4 pi epsilon naught Q divided by R square. Summation will be in the same, area will be in the same. So we have a sphere. So what should be the area of a sphere? If you remember, area of a sphere, which is equal to, I think so, it should be equal to 4 pi R square. So put out 4 pi R square here. Okay, once you put it out, so area is equal to 4 pi R square, area of a sphere. So the equation will be flux 1 divided by 4 pi epsilon naught will be in the same, Q divided by R square will be same. So on the point, on the place of area, we can put out 4 pi R square. So just solve the equation. Pi will cancel, R will cancel, 4 will cancel, and the result flux is equal to Q divided by epsilon naught. Okay, so one thing which is keep in mind, what is the relation between the flux and medium? So the flux and the relation of a medium, it is inverse. Once flux is going to increase, it means that the permittivity is going to be decrease. So this expression we can be write like this. Keep in mind, this most of the book you can be used like this. So flux is inversely proportional to the 1 by epsilon naught. So this expression shows that the total flux through the sphere is 1 divided by 4 pi epsilon naught times the charge enclosed in a sphere, and we can call this pair called a Gauss's law. We can call it Gauss's law. If somebody can ask you about a Gauss's law, so this proof is about Gauss's law. Okay, so what is the Gauss's law? Definition of Gauss's law is the total flux inside a closed surface. Keep in mind, the total flux inside a closed surface is equal to the 1 divided by epsilon naught time of the total charge inside a closed surface. Let's see, this pair is a closed surface. So what is Gauss's law? So Gauss's law is flux is equal to 1 divided by epsilon naught time the charge, total charge enclosed inside the closed surface, because it's a closed surface. So Gauss's law is always about a closed surface. Okay, so hope you got my point here. So coming to the electric flux density, we studied about electric flux. Now just a bit to talk about density. So simple definition, electric flux density is called electric displacement denoted by D, and is a vector field that appear in a Maxwell equation. So what is Maxwell? It's another concept, but just keep in mind it's about a Maxwell equation. So it is equal to the electric field. It is equal to the electric field strength multiplied by the permittivity of a material. Permittivity of material, we are not saying that the permittivity of free space, we are saying that permittivity of material through which the electric field extends. Okay, let's see, this is like you have a, this is kind of a surface. Okay, and we have a medium. This is a kind of a medium. It can be water, it can be paper, whatever. Okay, so when the electric field is going to be extend from the area, so this is called electric flux density. This is a simple concept. So it is measured in a coulomb per square meter. If you put out the unit of electric field intensity here and solve it out, so you will get this one. So the electric flux density is related to the electric field, and the formula is that electric flux density is always equal to the electric field strength multiplied by the permittivity of material. This equation is just simply shows that. So as according to the equation 1 about this, so we have a formula for the electric field, and electric field intensity is equal to Q1 divided by 4 pi epsilon, because you are not in epsilon, because you are saying that it's about material, it's about material. So for a material you are use epsilon. So Q1 divided by 4 pi epsilon r square, we have a formula for this. So we have a need to be put in the equation 1 for the electric flux density. So electric flux density is equal to, so epsilon will cancel out, so your result will be, so the electric flux density is equal to Q1 divided by 4 pi r square. So one thing keep in mind, now there is no relation between electric flux density and any permittivity, any material. So it means medium doesn't matter, doesn't so it, like we can say that electric flux density does not depend on the permittivity. Okay, so electric flux density does not depend on the permittivity because of this formula, as we proved that. So if you can see the electric flux density in equation 3, so electric flux density doesn't depend on the permittivity. Okay, so note that the field, the D field, the electric flux density is a vector field, which means that every point in space it has a magnitude and a direction. The electric flux density has a unit of a coulomb per meter square, as I told you before. So this was the lecture about electric flux and electric flux density, which is more important because when you are studying about some electric devices, so these things will be help you. So watch it out this video, and I'm hoping that it will help you. So once you have any question, just raise in the comments, so I will answer it to you. Thank you for your time. See you in the next lecture.